Good afternoon, everyone. Good afternoon. Good afternoon. Yeah, please let me know both audio and video are okay. Shall we start the session? Good afternoon, everyone. Good afternoon. Please let me know about the video and audio quality. Both are okay. Shall we start? Okay. So let us start with question number one. Okay. So this is the question number one. Right? Please read the question very carefully and try to answer these questions. Right? Read this question. The interrelationship between thermal conductivity, dynamic viscosity, and the temperature of a gas described by, right? So, thermal conductivity variation with temperature for gas and thermal conductivity variation with temperature for the gas. So, basically, in this question, that fluid is gas, not liquid, na? Right? Fluid is gas, right? So, in case of the gas, when you increase the temperature, then what happened with the thermal conductivity of the gas and what happened with the viscosity of the gas, right? What happened with the temperature of the gas and what happened with the viscosity of the gas. So as the temperature increases, thermal conductivity of the gas increases. Why thermal conductivity of the gas increases? Right? As temperature increases, thermal conductivity of the gas increases, right? Because, right, molecular momentum, or you can say molecular collision increases, right? Molecular collision increases. That's why thermal conductivity of the gas increases. And at the same time, that dynamic viscosity of the gas also increases, right? Dynamic viscosity of the gas also increases, right? And why dynamic viscosity of the gas increases? Because molecular momentum exchange increases as you increase the temperature. Right, so option number A says dynamic viscosity and thermal conductivity decreases as the temperature increases. So this is wrong option. Right, this is wrong option. Option B says dynamic viscosity decreases and thermal conductivity increases as temperature increases. Both having the same, you can say both having the same nature. Right, when temperature increases, both are increases, and then if temperature decreases, both are decreases. Dynamic viscosity and thermal conductivity decreases as temperature decreases. So correct option is option number C. Right, correct option is option number C. So when you decrease the temperature, when you increase the temperature, thermal conductivity and the viscosity increases, and when you decrease the temperature, then thermal conductivity of the gas decreases and also the dynamic viscosity of the gas also decreases. So correct option is option number C. Option number C is correct. Right, correct option is option number C. Fine, come to the next question. Come to the next question. We have a cylindrical fin of diameter 24 millimeter is attached horizontally to a vertical planar wall. The heat transfer rate from the fin to the surrounding air is 60% of the heat transfer rate if the entire fin were at the wall temperature. If the fin effectiveness is 10, then what about the length of the fin? Right? What about the length of the fin? Right? So basically in this question, length of the fin is asked. So we have the cylindrical fin na? And diameter is mentioned, that is 24 millimeter. Right, diameter is mentioned, that is 24 millimeter. Right, and what is given? The heat transfer rate from the fin to the surrounding air is 60% of the heat transfer rate if the entire fin were at the wall temperature. That means efficiency of the fin is given, and efficiency of the fin is 60%, that means 0.6, right? Effectiveness is given 10, right? And we know that the relation between the effectiveness and the efficiency, right? Effectiveness to efficiency, this ratio is surface area divided by cross sectional area, right? And effectiveness is given 10, efficiency is given 0.6, surface area is perimeter into length, so you can say pi into d L, and cross sectional area, that is pi by 4 d square, right? So pi cancel out, d and 1 d is cancel out, so ultimately this is 10, right? This is 10 upon 0.6 is equal to, this is 4L divided by d. So from here you can calculate the L, right? And length of the fin is asked in the millimeter. Length of the fin is asked in the millimeter. So tell me what is your answer, right? So this is 10.6 into diameter is given 24 millimeter, right? Diameter is given 24 millimeter, so it comes 100 millimeter, right? So correct option is correct answer is 100 millimeter. 100 millimeter is the right answer. Okay, yes, 100 millimeter is the right answer. Okay, come to the next question. So in this question, we have two very long concentric cylinders of dia 0.2 meter and 0.5 meter, maintain at uniform temperature 950 Kelvin and 500 Kelvin, and have emissivity 1 and 0.7 respectively. The net radiation heat exchange between the two cylinders is in watt per meter length. So this is the question. Okay, so basically we have two surface enclosure, right? In this question we have two surface enclosure, and this is the, let us assume this is the inner cylinder and this is the outer cylinder, right? And this is surface number 1 we assume, and this is the surface number 2, and radius is given, sorry, diameter is given. So radius is 0.1 meter, this radius is 0.1 meter, and this radius is 0.25 meter. So this is R1 and this is R2, right? And this emissivity epsilon 1 is 1 and the epsilon 2 is basically 0.7. So what is the net radiation heat exchange in two surface enclosures? So directly you can write the net radiation heat exchange between two surface enclosure, that is you can write this is A1 Fg12 sigma b T1 to the power 4 minus T2 to the power 4, correct na? And what is Fg12? That Fg12 is nothing but the interchange factor. Fg12 is the interchange factor, and this is 1 upon 1 minus epsilon 1 by epsilon 1 plus 1 upon F12 plus 1 minus epsilon 2 by epsilon 2, and this is A1 by A2. Right? Now epsilon 1, so epsilon 1 value is 1, so this term is 0. And F12, so F12 is 1, right? F11 is 0, right? And F12 is 1. So from here you can calculate the interchange factor. So Fg12, that is 1 upon, right? And this is 1 plus 1 minus 0.7, so this is 0.3 divided by 0.7 and A1 by A2. So the A1 by A2 is nothing but the R1 by R2, right? R1 by R2. So R1 is 0.1 and R2 is 0.25. So from here, first you calculate the interchange factor. First calculate the interchange factor. So this is 1 upon 1 plus 0.3 by 0.7 into 0.1 by 0.25. Right, so it comes 0.8536. This is the interchange factor. Now net radiation heat exchange, Q net is equal to, right, A1. So simply you can write this is a 2 pi R1L, right? Interchange factor we already calculated, Fg12 sigma B and T1 to the power 4 minus T to the power 4. Now put the value and get the answer. So net radiation heat exchange per unit length. So Q net per unit length, this is equal to 2 pi and R1 is 0.1, right? Fg12 is 0.8536 and Stephen Boltzmann constant 5.67 10 to the power minus 8. T1, so T1 value is mentioned 950. So 950 to the power 4 minus, this is 500 to the power 4. So from here you can calculate the net radiation heat exchange per unit length. So 2 pi into 0.1 into 0.8536 into 5.67 into 10 to the power minus 8 into 950 to the power 4 minus 500 to the power 4. So this comes 36450. Any mistake from my side? Right, any mistake from my side? Everyone getting interchange factor as 0.8536? Please check here. Everyone getting the interchange factor 0.8536? $950 na, 950 minus 500 to the power 4. Because I am getting the answer. My answer is 22868.558 watt per meter length. This is my answer. Right, 22868.55. This is my answer. सिलेंडर है ना, स्क्वायर क्यों होगा? सिलेंडर है ना तो स्क्वायर क्यों होगा? A1 by A2, if you calculate A1 by A2, this is cylinder na, so this is 2 pi R1L upon 2 pi R2L na, 2 pi cancel, L is cancel, R1 by R2. Why it is square? Right, this is not spherical, this is not spherical na, this is cylindrical na. एरिया कौन सा लेंगे? अरे एरिया कौन सा लेंगे? सिलेंडर है ना ये, ठीक है, सिलेंडर है तो सिलेंडर में रेडिएशन हीट एक्सचेंज ऐसा हो रहा है ना यार, ये ऐसा हो रहा है, तो रेडिएशन हीट एक्सचेंज किसके किसके बीच में रहा है? दिस इज द सरफेस 1 एंड दिस इज द सरफेस 2, right? The radiation heat exchange occurs between the surface 1 and surface 2. I am showing the side view actually. This is a side view, right? I am showing the side view. Right? Okay. See the next question. See the next question. For liquid ammonia, which is at 20 degrees Celsius, thermophysical properties are dynamic viscosity you have, specific heat is given, thermal conductivity is also given. If hydrodynamic boundary layer thickness is 0.8 millimeter, then the thermal boundary layer thickness is. And in question it is clearly mentioned, assume laminar condition. Right. So this is a problem of, right, this is a problem of convection. Right. And question it is clearly mentioned the hydrodynamic boundary layer thickness is 0.8 mm. Then what is the thermal boundary layer thickness? So this is a problem of, right, this is a problem of laminar external force convection. So delta Hx by delta Tx is equal to Prandtl number to the power 1 by 3 na? Prandtl number to the power 1 by 3. Now calculate Prandtl number, because Prandtl number is not given, and Prandtl number is, this is mu Cp by Kf, right, and dynamic viscosity is given 14 into 10 to the power minus 5 into specific heat, this is 4.798 into 10 to the power 3 joule per kg degree Celsius, and thermal conductivity is given 0.521. So from here you can calculate the Prandtl number. Right, so this is 14 into 10 to the power minus 5. 14 into 10 to the power minus 5, 4.798 into 10 to the power 3 divided by 0.521. So I think Prandtl number comes 1.289. Right, so delta Hx, so hydrodynamic boundary layer thickness is given, that is 0.8 mm. Thermal boundary layer thickness is asked, right? So this is 1.289 to the power 1 by 3. So this comes 0.8, 1.289 to the power 1 by 3. So it comes delta Tx, this comes 0.735 millimeter. Please check. 0.735 millimeter. This is the thermal boundary layer thickness. Yes, 0.735 millimeter. Absolutely correct. Yes, if laminar is not mentioned, then definitely you must calculate the Reynolds number. And once you know the Reynolds number, then on the basis of Reynolds number, we can comment it is a laminar or turbulent. So if it is not mentioned laminar, then we have the sufficient data in the problem so that we can calculate the Reynolds number. Fine. Come to the next question. Okay. For heat transfer across a solid fluid interface, which one of the following statement is not true? Right, which one of the following statement is not true? Please read the question very carefully. Right, which statement is not true? When the Biot number is very small compared to 1. So when the Biot number value is very small, then which of the following statement, which one of the statement is not true? So statement A says conduction resistance in the solid is very small compared to the convection resistance. We know that if Biot number value is very small, right, if Biot number value is very small, then internal conduction resistance is very small than external convection resistance. Correct na? So statement A says conduction resistance in the solid is very small compared to the convection resistance of the fluid. So this statement is true actually. This is true. Right, this statement is true. Now temperature profile within the solid is nearly uniform. Right, this is also true. Within the solid there is no temperature gradient. So statement B is also true. Statement C, temperature drop in the fluid is significant. Definitely. Right, temperature drop in the solid fluid interface is significant. So this statement is also true. So which statement is wrong? In this question, what is asked? Which statement is not true? So basically, which statement is false? So statement D, temperature drop in the solid is significant. So this statement is, right, for this statement is false. Right, this is false. And for this question, correct option is option number D. For this question, correct option is option number D. But this is not MSQ question, this is the MCQ question. Right, this is not MSQ question, this is MCQ question. This is MCQ, not MSQ. So only one option is correct. And in this question, it is clearly mentioned which statement is not true, or you can say which statement is false. So this statement is true, this statement is true, this statement is also true. So which one is the correct option? Correct option is option number D. D is the correct one. Okay, now see the next question. So we have the thermocouple. Thermocouple indicates a steady temperature of 600 degrees Celsius when it is placed in a duct where a hot gas is flowing at 720 degrees Celsius. The convective heat transfer coefficient between the thermocouple and the gas is 60 watt per meter square Kelvin, and emissivity for the thermocouple junction is 0.5. Question is, what is the duct wall temperature? Right, what is the duct wall temperature? This is the question. Okay, so thermocouple indicates a steady temperature. So reading of the thermocouple, that means junction temperature is 600 degrees Celsius. Right, thermocouple indicates a steady state temperature of 600 degrees Celsius. So whatever the temperature shown by the thermocouple, that is nothing but the reading of this junction only. Right, so junction temperature is given, and junction temperature is 600 degrees Celsius. And when it is placed in a duct where hot gas is flowing, so hot gas temperature is mentioned. Hot gas temperature is mentioned, and that temperature is 720 degrees Celsius. Right, convective heat transfer coefficient, here the H value is mentioned, and that H value is 60 watt per meter square Kelvin. So question is, what is the wall duct temperature, and the emissivity is given 0.5. So basically this duct is a long duct, it is also mentioned. Right, this duct is long duct. This is long duct. Okay, now at steady state condition, it is clearly mentioned steady state. So at steady state, it is clearly mentioned steady state. So if you consider this junction as a system, and if you apply, right, if you apply the energy balance for this system, so energy balance, can you write energy balance? So if you write the energy balance for this system, so simply you can write that energy in plus energy generated is equal to energy out plus change in internal energy with respect to time. Right, and in this question it is clearly mentioned steady state condition is there, so this term is 0, and in this system there is no heat generation, so this term is also 0. So at steady state condition, simply you can write rate of energy in is equal to rate of energy out. Right, rate of energy in is equal to rate of energy out. Okay, now tell me what is the energy in, right? What is the energy in this system? So the energy in this system is via convection. Right, the energy in this system is via convection. So simply you can write that energy in is nothing but the convection heat transfer between between gas and junction. And what is the energy out? So the energy out is nothing but the radiation that occurs between the junction and the wall, right? So that is equal to radiation heat exchange, radiation heat transfer between junction and the wall, between junction and the wall. So what is the convection heat transfer between gas and the junction? So simply you can write this is H into area of junction, and this is temperature of the hot gas minus temperature of the junction, right? This is the convection heat transfer between the hot gas and the junction, and this is equal to radiation heat between junction and the wall. So basically this junction is something like a small body in a large enclosure. So whenever a small body in a large enclosure, then what is the radiation heat exchange? So the radiation heat exchange is, this is A into epsilon, right? A into epsilon sigma B, right? And this is T junction to the power 4 minus, right? And this is T wall to the power 4. Right, so this is the radiation heat exchange between the junction and the wall, right? So it is a case where a small body is a large enclosure, right? So area of junction is cancelled out. Now H value is given, H value is 60, right? And hot gas temperature is 720 minus junction temperature is 600, and this is equal to, right, junction emissivity 0.5 and Stephen Boltzmann constant 5.67 into 10 to the power minus 8, right? And junction temperature is 600. So first convert into Kelvin, na? 600 plus 273, so it is 873 to the power 4 minus, and this is wall temperature to the power 4. Okay, now calculate the wall temperature. 483. Okay, let me check. So 60 into 720 minus 600, 120. 0.5. 5.67 into 10 to the power minus 8. Okay, minus 8. And this is 873 to the power 4 minus answer 1 by 4. My answer is 756, right? I'm getting 756.126, and this is in Kelvin. Okay, in degree Celsius ask na. Okay, so this temperature TW, this is 756.126, this is in Kelvin, right? And in degree Celsius, so minus 273. Yes, it is 483. It is 483.126 degrees Celsius. So this is the right answer. Yes, right, 483.126. 483.126 degrees Celsius. This is the right answer. So beta, this type of question definitely you can expect in your exam, right? So in this problem actually multi-mode heat transfer is involved. So whenever in the problem multi-mode heat transfer is involved, such type of problem is important for exam point of view, right? Because here it is convection occurs, then in between there is a in between the wall and the junction there is a radiation. So whenever in the problem multi-mode heat transfer is involved, so such type of problem is important as per the competitive exam point of view, right? So this is one of the good problem, right? Is it clear to everyone? Is it clear here? Fine. Come to the next question. Okay, so we have the steel ball, right? Steel ball diameter is 10 millimeter, is 10 millimeter dia, initially at 900 degrees Celsius, is placed in air at 30 degrees Celsius. And for steel, we have the information, density is given, specific heat is given, right? Thermal conductivity, convective heat transfer coefficient is given. Question is, what is the instantaneous rate of heat transfer? Instantaneous rate of heat transfer at 30 second. Okay, at time t is equal to 30 second, what is the rate of heat transfer? So basically this is a problem of transient conduction, right? This is the problem of transient conduction. And if you calculate the Biot number, so Biot number is basically, this is HLC by Ks, and this is a ball, na? So that is characteristic length is d by 6. So simply you can write this is h by Ks into, and this is d by 6. Correct? So Biot number, h value is given, h value is 20, diameter is 10 millimeter, so 0.01 divided by thermal conductivity is given 40 into 6. So Biot number value, right, this is 20, right, this is 20, 0.01, and this is 12. So this value comes 0.008, right, this is 0.008, even 0.0083, which is less than 0.1. So lumped system analysis is applicable, right? Lumped system analysis is applicable, and lumped system analysis is applicable, right? So directly in this question, what is asked? What is the instantaneous heat transfer? So instantaneous heat transfer, you can write that is H into A, and this is T minus T infinity, no? Right? This is the instantaneous heat transfer, right? Now calculate the temperature. Temperature at time t is equal to 30 seconds. So directly use relation T minus T infinity upon Ti minus T infinity is equal to, this is e to the power minus HA rho Vc into tau, or you can write e to the power minus H into tau, and this is rho C, and this is LC, right? So T minus T infinity, ambient temperature is 30, initial temperature is 900, minus 30, e to the power minus H value is 20 watt per meter square Kelvin, 20 time 30 divided by rho value is given 7800 into specific heat is given 460, and V by A, that is the characteristic length, so D by 6, right? So 6 into diameter is given 0.01, right? Now do one thing, e to the power minus 20 into 30 into 6, 7800, 460.01 into 900 minus 30. So this is plus 30. So I think it comes, temperature is 816. Beta, please check the calculation now. 816.914 degrees Celsius. This is the temperature when time is 30 seconds. Everyone getting this? Everyone getting this? So this is a temperature, and instantaneous heat transfer is asked. So H value is 20, right? And the area from where heat transfer occurs, so that is surface area. So 4 pi r square, so that is 5 mm, so 0.005. square into, and this is T minus T infinity. So 816,945 minus 30. 816.945, yes. So it is 20 into 4 pi 0.005 square into 816.945 minus 30. So I think it comes 4.95. It comes 4.95 watt. Please check here. It comes 4.95 watt. Please check. Right? Everyone getting this, now? Yes. Right? 4.944 watt. Okay. See the next question. Okay, so heat is generated at a steady rate of 200 watt due to resistance heating in a long wire, right? So wire is there having thermal conductivity 0.2 watt per meter Kelvin. Length dia is 5 meter, 2 millimeter respectively. Wire is wrapped with an insulation of thickness 1 mm that has thermal conductivity 0.1 watt per meter Kelvin. The insulated wire is exposed to the air at 30 degrees Celsius. Convective heat transfer coefficient between the wire and the surrounding is 10 watt per meter square Kelvin. Question is, what is the maximum temperature? Right? What is the maximum temperature? Okay, so we have the cylindrical wire. Length is perpendicular to the monitor. And in this wire, we have the insulation. Right? So this is the insulation. Right? And this radius is 2 millimeter. This is 2 millimeter. And insulation having thickness 1 mm. So this is R2, let us assume. Okay, so this radius is R1. This radius is R2. So R1, right? R1 is given length and dia 5 meter 2 mm. So R1 is 1 mm and R2 1 plus 1. So this is 2 mm. Right? This is R2. Okay. Thermal conductivity of insulation is given. So thermal conductivity of insulation, that is 0.1 watt per meter Kelvin. And the wire thermal conductivity is wire thermal conductivity is 0.2 watt per meter Kelvin. Okay, and heat is generated at a steady rate of 200 watt, right? So total heat generation is given, right? Total heat generation is given, and that is 200 watt. So question is, what is the maximum temperature? So the maximum temperature, right, in the wire, heat generation occurs. So maximum temperature occurs at the center, na? Maximum temperature occurs at the center, and this is a uniform heat generation case basically, right? Uniform heat generation case. But here total heat generation is given. So do one thing, first find out the volumetric heat generation. So the volumetric heat generation, you can write total heat generation divided by, right, volume. So this is pi by 4 d square into L. So pi by 4 d square, diameter is 2 millimeters. So pi by 4 d square into length, and length is given 5 meter. So this is the heat generation per unit volume, right? So this is 200.785.002 square into length is 5 meter. So I think this comes 12.73 or 12.74 megawatt per meter cube, right? Please check beta, right? 200 watt, pi by 4 d square, diameter of the wire is 2 millimeters, so that is 0.002, right? And this is 5. Okay, length is 5, pi by 4 d square into L. Okay, so this is the heat generation per unit volume, right? And once you know the heat generation per unit volume, so what is the maximum temperature? So maximum temperature occurs at the center, and we know that for solid cylinder, if you write temperature variation with respect to R, so you can write this is TW plus Q dot G by 4K capital R square minus small r square, right? And in this case, TW, so TW is nothing but the temperature here. This is the TW. This is the TW, right? And R1, instead of R, there is a R1, right? And instead of K, there is KW, that is wire thermal conductivity, right? So you have, right, so you have maximum temperature. So at R is equal to 0, T become T max, right? So maximum temperature is equal to TW plus Q dot G by 4KW, and that is R1 square. Now see this equation. If you see this equation, Q dot G is known, right? This is the Q dot G. Q dot G is known. R1 is known. R1 is 1 millimeter, right? KW is known. KW is given 0.2 watt per meter Kelvin. The only unknown thing is TW. Without calculation of TW, we cannot calculate the maximum temperature. So how you calculate this TW? How you calculate this TW? Right? So whatever the heat generation occurs in the wire, right, that dissipated in the ambient, that dissipated to the ambient, and ambient condition is given, right? Ambient condition is given, and ambient condition, right, T infinitive, let us assume ambient temperature is T infinitive, that is 30 degrees Celsius, and the convective heat transfer coefficient is, that is 10 watt per meter square Kelvin, right? So TW is unknown basically. So if you draw the thermal circuit here, so this temperature is TW, and this is the conduction resistance of the insulation, and this is outside convection resistance, right? This temperature is TW, this temperature is T infinitive, and this is the insulation conduction resistance, and this is outside convection resistance, right? And what is the heat generation here? That is 200 watt. So 200 watt, whatever the heat generation occurs, that flowing through this circuit. So simply you can write, right, simply you can write, because TW is unknown, for me TW is unknown, so simply you can write that Q dot, which is a heat generated, is equal to TW minus T infinitive upon, and what is the conduction resistance of the insulation. So this is ln R2 by R1 upon this is 2 pi KIL plus this is 1 upon H into this is 2 pi R2L. So Q dot is 200, TW is unknown, this is 30 into 2 pi into L is given 5 meter upon, right, L is given 5 meter, ln this is 2 by 1 upon KI value is 0.02, sorry 0.2, I'm sorry, plus this is 1 upon H value is given 10 and R2 value is given 2 millimeter, that means 0.002. Now calculate TW from here. Tell me what is TW, and once you know TW, right, once you know the TW, you can easily calculate the T maximum. Now tell me what is TW. What is TW? What is TW? So this is 200 into, or this is ln, just 1 minute, 200 into ln 2.2 plus 1 upon 10 into 0.002, right, and this is 2 pi into 5 plus 30. I think it is 370. TW is 370.373. Please check here. TW is 392. Okay, just 1 minute. I think TW, this is 200 into 200 into, and this is ln 0.2 plus 1 upon 10 into 0.002. And this is 2 pi 5. Okay, this is 340. 340 plus 30. But I'm getting 370.373 TW. Please check here. I'm getting this answer. Please check, everyone getting this? Now tell me T maximum. So T maximum TW 370.373 plus Q dot G, which is heat generation per unit volume, 12.74 10 to the power 6 upon 4 multiplied by KW, and wire thermal conductivity is 0.2. I think just 1 minute. I think there is an error. Insulation thermal conductivity is 0.1. I'm sorry, beta. Insulation thermal conductivity is 0.1, na? So by mistake, just 1 minute. Insulation thermal conductivity is 0.1, na? Not 0.2. Yes. This is 0.1, na? Tell me what is TW. Now tell me what is TW. Yes. Insulation thermal conductivity is 0.1. That is my mistake. Insulation thermal conductivity is 0.1. Now tell me what is TW. So TW, what is your answer, guys? TW is ln 2.1 plus 1 upon 10 into 0.002, right? And 392.437 degrees Celsius, right? So this is 392.437 and 12.74 into 10 to the power 6, 4 into kW. kW value is 0.2 into R1 square, and R1 square, R1 is 1 mm, right? 1 mm. So 1 square into 10 to the power minus 6. So this is cancel out. Plus 12.74 into 1 and 4 into 0.2. So 408, yes. So maximum temperature comes 408.36 degrees Celsius. This is the maximum temperature, right? This is the maximum temperature. Yes, this is the maximum temperature. 408.53 or 36 degrees Celsius. This is the maximum temperature. Is it clear? Okay. Now see the next question. So two spherical bodies, radius 6 centimeter and radius 18 centimeter, are at temperature T1 and T2 respectively. The maximum intensity in the emission spectrum of A is at 500 nanometer and is that of B is at 1500 nanometer. Considering them to be a black bodies, ratio of rate of total energy radiated by A to that of B is, right? So question is ratio of the rate of total energy radiated by A to that of B, right? So total radiation energy emitted by body A to total radiation energy emitted by body B, and this is equal to, so we know that, right, radiation energy emitted by a black body is directly proportional to, right, A T to the power 4, right? And obviously this is in watt, no? This is in watt. In watt per meter square, it is directly proportional to T to the power 4, because here the radius is mentioned. So you can write this is A T to the power 4 for A upon A T to the power 4 for B, and both are spherical. So area, simply you can write pi 4 pi r square. So you can say this is r square T to the power 4 A upon r square T to the power 4 and B. So you can write this is RA by RB, RA by RB to the power 2 and TA by TB to the power 4. Okay, and also in this question, what information we have? The maximum intensity in the emission spectrum of A is 500 nanometer. Okay, so we know that lambda m into T is equal to constant, no? Right? Lambda m into T is equal to constant. So we can write lambda m for A, TA is equal to lambda m B and temperature B. So TA by TB, TA by TB is equal to lambda m B upon lambda m A. And lambda m B, for B it is 1500 and for A it is 500. Right, so 5 ones are 5 threes are. So this is TA by TB, that is equal to 3. So RA radius A, this is 6, RB 18 square, and TA by TB, that is 3 to the power 4. So 6 ones are 6 threes are. So this is 1 upon 3 square and this is 3 to the power 4. So what answer you are getting? 3 square, that means 9. This is answer. Yes. Right. So correct option is option number. Sorry, correct answer is 9. 9 is the right answer. Okay. Now see the next question. Sir, it's getting hard to remember the formulas. But beta, we don't have any options. We must remember the formulas. Right? We don't have any options. The only solution for this, right? Revise multiple times. Right? This is the only solution we have. So basically, we have long cylindrical iron wire. Thermal conductivity is 80 watt per meter Kelvin is exposed to the ambient after heat treatment. For the lumped capacitance model to be valid, the maximum wire diameter. What is the maximum wire diameter? So we know that to apply the lumped system analysis, Biot number value should be less than 0.1. And Biot number is simply HLC by KS. Right. H value is mentioned, that is 400. And LC. So in this question, it is clearly mentioned long cylindrical iron wire. Right. So cylindrical wire is long. So directly we can write R by 2 or D by 4. Directly we can write. So LC is equal to D by 4 into thermal conductivity of the wire, that is given 80, less than 0.1. Right. So 4 and this is right. So this is 10 by 8. 10 by 8 times of dia, and less than this is 1 by 10. So when you cross multiply that D, right? So 10 D, or you can say 100 D, and this is 8. So D less than 8 by 100, right? So this comes in meter. Answer is asked in the millimeter. So this is 1000 millimeter. So 0, 2, 0 cancel out. So diameter less than 80 millimeter. Diameter less than 80 millimeter. So what is my question? My question is maximum wire dia. Right? Maximum wire dia. My question is maximum wire dia. So the maximum wire dia is 80 mm. Maximum wire dia is 80 mm. Yes. Maximum wire dia is 80 millimeter. This is the answer. Okay, now see the next question. Water is flowing in a steel pipe of dia 0.02 meter is to be cooled from 40 to 30. 40 degrees Celsius to 30 degrees Celsius. Velocity of the water in the steel pipe is 1.5 meter per second. The inside surface temperature of the steel pipe is maintained at 25 degrees Celsius. Physical properties of the water are. Okay. Question is, what is the convective heat transfer coefficient? What is the convective heat transfer coefficient? This is the question. Right. So convective heat transfer coefficient is asked now. right? So first recall your concept. So this is a problem of internal force convection, right? This is a problem of convection, and this problem is based on the internal force convection because water is flowing in the pipe. So this is a problem of internal force convection. Now in this question, convective heat transfer coefficient is asked, right? Now yes, first calculate the Reynolds number. Exactly, first calculate the Reynolds number. First try to find out the flow condition in the pipe, है ना? First try to find out the flow condition in the pipe, and on the basis of flow condition, then you can use the Nusselt number expression, na? Then you can use the Nusselt number expression. So this is a simple question actually, right? If you calculate the Reynolds number, so Reynolds number is nothing but this is rho u average d divided by this is mu. So density is mentioned. Density is given 985 kg per meter cube into velocity is mentioned 1.5 meter per second. Diameter is mentioned. Diameter is 0.02 meter divided by, and viscosity is given 7.6 into 10 to the power minus 4. Right. So what is the Reynolds number? 985 into 1.5 into 0.02, 7.6 into 10 to the power minus 4. So it comes 3881.58, right? So which is greater than critical Reynolds number. So flow is turbulent. Flow is turbulent flow. And whenever the flow is turbulent flow, right? Whenever the flow is turbulent flow, whenever the flow is this is Reynolds number now. Whenever flow is turbulent flow, and that is the internal force convection. So we have the Dittus-Boelter equation. So use Dittus-Boelter equation. Now see, in this question, Dittus-Boelter equation is not given. So you must remember Dittus-Boelter equation. Dittus-Boelter equation. And Dittus-Boelter equation says Nusselt number, this is HD by KF is equal to 0.023. Reynolds number to the power 0.8 and Prandtl number to the power, right? Cooling of the fluid occurs, na? Cooled from, yes. So Prandtl number to the power 0.3. Right, Prandtl number is not given. So calculate the Prandtl number. So Prandtl number is mu Cp by Kf. Right, mu value is given 7.6, 10 to the power minus 4 into Cp value is given 4.18 into 10 to the power 3 joule per kg Kelvin upon thermal conductivity of the fluid 0.63. So calculate Prandtl number from here. And once you know the Prandtl number, then you can easily calculate the convective heat transfer coefficient. So 7.6, 10 to the power minus 4 into 4.18, 0.63. So I think it comes 5.0425. This is Prandtl number. Now H into diameter 0.02 upon thermal conductivity 0.63, 0.023. Reynolds number value is 3881.58 to the power 0.8 and Prandtl number is 5.04 to the power 0.3. So from here you can calculate the H. One equation, one unknown. So tell me what is H. Okay, so almost everyone getting 5528.76. 5528.76 watt per meter square Kelvin. Sir, when we use the hydraulic dia, right? Hydraulic dia, when you have the non-circular cross section, na? When you have the non-circular cross section, so hydraulic dia is, this is 4 into cross sectional area divided by weighted perimeter, na? And in case of the circular pipe, in case of the circular pipe, your DH is nothing but the D only. So 4 into cross sectional area pi by 4 D square upon weighted perimeter is pi D. So pi cancel out, 4 cancel out, D and D cancel out. So in this case, DH is D only, na? In this case, DH is D only. So whenever you have the circular cross section pipe, so your hydraulic dia is the diameter only. But when you have the non-circular cross section, right, when you have the non-circular cross section, at that particular case, you must calculate the hydraulic dia. Right? In this case, your hydraulic dia is the diameter of pipe only. Fine? Okay. Okay. क्रिटिकल रेनॉल्ड नंबर 4000 होगा. अरे क्या कर रहे हो? क्रिटिकल रेनॉल्ड नंबर 4000 होगा. क्रिटिकल रेनॉल्ड नंबर 4000 कहाँ होता है मेरे भाई? इंटरनल फ्लो के केस में द क्रिटिकल रेनॉल्ड नंबर इज 2000. if Reynolds number value is less than 2000, your flow is laminar. In between 2000 to 4000 there is a transition. If Reynolds number is greater than 4000, then we take that flow as a turbulent flow. Okay, so in this question we have the cylinder of radius r is surrounded by a cylindrical shell of inner radius 2r. So basically you have the cylinder, and this cylinder having radius r, and it is surrounded by a cylindrical shell, and this cylindrical shell inner radius is 2r. So basically it is something like this. Right, it is something like this. Right, and thermal conductivity of the material of the cylinder is K1, and that of the outer cylinder is K2. Right, the effective thermal conductivity of the system for heat flowing along the length of the cylinder. Now tell me, what is this connection? Is a parallel connection or series connection? This connection is a parallel connection or series connection? This is a parallel connection, na? This is the parallel connection, na? Heat is flowing along the length, so this is a parallel connection. And in the case of parallel connection, we know that K equivalent is equal to K1 A1 plus K2 A2 upon A1 plus A2. Okay, so K equivalent is equal to K1 is K, sorry, this is K1, na? K1 into area, so that is area which is normal to direction of conduction heat transfer. So this is pi r square, right? And K2 into A2, so A2 is pi, and this is 2r square, this radius is 2r, so 2r square, that means 4r square minus r square divided by, right, pi r square plus pi and 4r square minus r square only. Right, so the K equivalent is, right, pi r square, so this is K1 plus, and this is 3K2 upon, right, and pi r square, and this is 3 pi r square, so this is 4. So K1 plus 3K2 by 4. So correct option is option number, yes, correct option is option number D. Option number D is correct. Right, correct option is option number D. D is correct one. Okay, now this is the MSQ question. Right, this is the MSQ question. Okay, the steady state temperature distribution in a composite plane wall of three different materials, each of constant thermal conductivity, is shown. Which of the following statement is are correct? Okay, now the interface at 4 is adiabatic. Now interface at 4 is adiabatic. So this is interface 4, right? And interface 4 is adiabatic. Yes, it is adiabatic because if you see here the slope is 0, right? If you see here the slope is 0, here the slope is 0. So the interface 4 is adiabatic. So whenever the face is adiabatic, so dt by dx is 0. So in this here, if you see dt by dx is a 0, right? So interface 4 is adiabatic, absolutely correct. The volumetric heat generation occurs in the wall C. Yes, in the wall C, the volumetric heat generation occurs. If there is no heat generation, then the temperature profile is linear. But in this case, if you see the wall number C, in the wall number C, uh, uh, temperature profile is non-linear. There is a something parabolic kind of temperature profile. So definitely yes, volumetric heat generation occurs in the wall C. So B is also correct. The heat flux in C increases with decreasing X. Heat flux in C heat flux in heat flux in C increases with the decreasing X. Yes, so as we are moving in this direction, right, decreasing X, right, this is the X direction basically. So as we are moving in the X direction, as we are moving in opposite to the X direction, right, or you can say as we are moving in the decreasing X direction, the heat flux increases. Why heat flux increases? Because slope increases, dt by dx. So dt by dx is increases. Here dt by dx value is 0, and as we are moving in the negative X direction, dt by dx increases. So definitely yes, the heat flux in C increases with decreasing X. Correct. Now K is greater than KB. Now if you see the slope, right, if you see the slope, right, if you are observing this, right, in this case here slope is theta B, here the slope is theta A, and theta A is greater than theta B. So if theta A is greater than theta B, that means Ka is lesser than Kb. Ka is lesser than Kb. So option number D is wrong. Right, option number D is wrong. Option number D is wrong. Right, so correct option is A, B, C. A, B, C. These three statements are correct. X is not given. हाँ बेटा अब देख लो थोड़ा सा, ठीक है, टाइपिंग एरर हो गया होगा, है ना, बट समझ तो आ ही रहा है ना, ये एक्स डायरेक्शन होगा, ये वाई डायरेक्शन होगा, ठीक है, टाइपिंग एरर हो गया होगा, ठीक है, कोई बात नहीं. So basically this is the x direction. ठीक है. Now see the next question. Okay, so we have the plain wall of thickness 40 millimeter thickness. We have the plain wall of 40 millimeter thickness. And in this plain wall, uniform heat generation occurs. Right, uniform heat generation occurs, and also it is mentioned, right, wall material has thermal conductivity 20 if the side surfaces are maintained at 450 Kelvin. That means here the temperature is 450 Kelvin. Here also temperature is 450 Kelvin. So basically this is a symmetric condition problem. Right, this is a symmetric case problem. So maximum temperature occurs at the mid plane. Right, maximum temperature occurs at the mid plane. Okay, now question is maximum temperature is given. Question is what is the heat generation per unit volume. So question is what is Q dot G. So basically this is a standard problem. This is a standard problem. So directly you can write this is temperature variation with respect to x, and this is your x direction beta. So temperature variation with respect to x, that is equal to TW plus this is Q dot G by 2K, and this is delta x minus x square. Right, and maximum temperature occurs at x is equal to delta by 2 at x is equal to delta by 2. Right, T become T max. So directly you can write T maximum is equal to TW plus this is Q dot G by 8K, and Q dot G by 8K, and this is delta square. Q dot G by 8K delta square. Now T maximum is given, T maximum is 1000 Kelvin. This is 450 Kelvin plus Q dot G is unknown upon 8 multiplied by thermal conductivity is given 20 watt per meter Kelvin into thickness 40 millimeter, delta is 40 mm. So this is 0.04 square. So if you calculate, everyone getting D, so I'm directly writing the Q dot G. This is 55 megawatt per meter cube. 55 megawatt per meter cube. So this is formula based question. 55 megawatt per meter cube. Direct formula based question. Yes, D is correct. Okay. Try to solve this question. Okay, so we have two circular surfaces A and B with the values of emissivity, epsilon, temperature T, and respective view factor are shown in the figure. Right, consider heat radiation only between surface A and surface B. So basically heat transfer occurs between these two surfaces. So basically this is two surface enclosure kind of thing. Stephen Boltzmann constant is given 5.67 into 10 to the power minus 8 watt per meter square Kelvin to the power 4. Net heat flow rate by radiation from surface A in kilowatt is. So calculate net radiation heat exchange basically. Right, so net radiation heat exchange. Right, directly you can write this is A1 Fg12 sigma B T1 to the power 4 minus T to the power 4. Correct na? Now what is Fg12? So Fg12 is interchange factor, and this is 1 upon 1 minus epsilon 1 by epsilon 1 plus 1 upon f 1 2. So let us assume this is 1 na? This is 1 and this is 2. Instead of AB we can use 1 and 2. So 1 upon f12 plus 1 minus epsilon 2 by epsilon 2, and this is A1 by A2. Right? So interchange factor FG12, and that is equal to 1 upon 1 minus epsilon 1. So 1 minus epsilon 1. So this is 1 minus 0.7. So this is 0.3 by 0.7 plus F12. So that is given 1 upon 0.172 plus and 1 minus epsilon 2. So this is 0.2 divided by 0.8 into, and this is R1 by R2 whole square. R1 by R2 whole square. Right? So A1 by A2 is nothing but the pi R1 square upon pi R2 square na? Right? Okay. So tell me what is FG12? What is FG12? Tell me what is FG12? So that A1 by A2, A1 by A2 is simply R1 by R2 square. Now tell me what is FG12? What is FG12? Please tell me. And once you know the FG12, now you can easily calculate the net radiation heat exchange. So that is equal to A1. So A1 is, this is pi R square into, right? Now tell me what is FG12 here? FG12 value 0.1540. Yes, 0.1540. 0.1540. Right? FG12. And sigma B 5.67, 10 to the power minus 8. T1, and T1 is 800 to the power 4 minus, this is 500 to the power 4. So from here you will get in watt, and answer is asked in the kilowatt. So what you are getting, 9 point. Who says this formula is for infinitely parallel plate? 9.523. 9.523 kilowatt. Right, this is answer. But this formula you can use for any two surface enclosure. In case of the parallel plates, it is 1 upon 1 by epsilon 1 plus 1 by epsilon 2 minus 1. Okay. Okay, now this question is again MSQ. Okay, MSQ question. Next question is MSQ. Air flowing with a velocity of 30 meter per second enters an annulus of ID 40 millimeter and OD 60 millimeter. That means inner dia and the outer dia at a temperature of 25 degrees Celsius. The temperature of the outer surface of the inner tube, okay, is maintained at constant temperature of 75 degrees Celsius. Fine. The exit temperature of the air is 50 degrees Celsius. Okay. The properties of the air corresponding to 56.25 degrees Celsius are, okay, so we have the properties. Which of the following statement is correct? So the air temperature variation in the axial direction is parabolic, In annulus, airflow is laminar, convective heat transfer coefficient and length of the annulus required for heating the air. So basically that flow occurs in the, right, this is the inner, right, this is the inner tube, you can say, and this is the outer one. Right, and the flow occurs in the annulus of inner and the outer cylinder. Flow occurs in this passage. So this dia is mentioned that ID is 40 mm, inner dia is 40 mm, and the outer dia, this 60 mm. Okay, and the, right, air is flowing air flowing with velocity of 30 meter per second. So here velocity is 30 meter per second. Okay, at a temperature 25 degrees Celsius. So here the mean temperature at the inlet, this temperature is 25 degrees Celsius. The temperature of the outer surface of the inner tube is maintained at temperature 75 degrees Celsius. So basically this temperature Ts, right, or you can say Ts is maintained at 75 degrees Celsius. Okay, and exit temperature of the air, that means TME, this is 50 degrees Celsius. This is 50 degrees Celsius. Okay, so this is the problem of constant wall temperature condition. Na? This is the problem of constant wall temperature condition. And in the constant wall temperature condition, the fluid temperature, how the mean temperature of the fluid changes exponentially, not parabolically. Right, this is a constant temperature wall condition problem. And in constant wall temperature condition problem, if you see, if you draw the temperature versus X plot, if you draw the temperature versus X plot, so this is X, this is temperature, right, and wall temperature is higher than the TMI, so this is TW, and the mean temperature of air changes exponentially. So it is something like this, right? This is TMI, this is TME, and this variation is exponential. This is exponential variation. So the correct option number A is wrong. Well, statement A is wrong. Statement A is wrong. Right, air temperature variation in the exact direction is parabolic. Okay, in annulus flow is laminar. So for that, first calculate the Reynolds number. Okay, in this case, calculate the hydraulic dia. And hydraulic dia is 4 into AC divided by weighted perimeter, and this is 4 into pi by 4 d naught square minus di square upon weighted perimeter. So this is pi d naught plus di. Right, so what you are getting, hydraulic dia, this is simply d naught minus di. Right, this is the hydraulic dia. 4 cancel out, pi cancel out, a square minus b square, a minus b, a plus b. So d naught minus di, and d naught value is 60 minus 40. So this is 60 minus 40. This is 20 mm. Right, 20 mm. Now calculate the Reynolds number. So Reynolds number is, this is rho u average dh divided by mu. Right, density is mentioned. Yes, density is given 1.07. velocity is mentioned and velocity is given 30 meter per second. Hydraulic dia is 20 into 10 to the power minus 3 divided by dynamic viscosity. Dynamic viscosity is given 19.8 into 10 to the power minus 6 kg per meter second in Pascal second only. 19.8 into 10 to the power minus 6. So from here you can calculate the Reynolds number. Okay, so 1.07 into 30 into 20 into 10 to the power minus 3. 19.8 into 10 to the power minus 6. Beta, please check, everyone getting this? 324.24, right, which is greater than 2000. Right, this is also internal flow. So flow is turbulent. Please check, everyone getting this? Flow is turbulent. Flow is turbulent. Flow is turbulent. So statement B is also wrong. In annulus, flow is laminar. This is also wrong. Okay, now convective heat transfer coefficient. So to find out the convective heat transfer coefficient, yes, to find out the convective heat transfer coefficient, Reynolds number we know that, constant wall temperature condition, right? We have the Dittus-Boelter equation, right? So Nu, and this is Nusselt number, this is HDH. HDH by Kf is equal to 0.023 Reynolds number to the power 0.8 and Prandtl number to the power 0.3 or 1 by 3, no issue. Okay, now calculate H. Calculate H. Okay, so hydraulic dia is 20 millimeter, na? So H into, this is 0.02 divided by Kf. Thermal conductivity of the fluid is mentioned, that is thermal conductivity is 0.028. That means 0.03, you can say 0.028, 0.023, and Reynolds number 32424.24 to the power 8, 0.8, and heating of the fluid occurs, na? So this is 0.4, you can take, no issue. 0.4. Answer not very much, na? Right, and Prandtl number is given. Prandtl number is given, yes, it is given 0.7. 0.7 to the power 0.4. Now tell me what is H. Tell me what is H. Okay, tell me what is H. What answer you are getting? That is H. Now next one is length of the annulus. So length of the annulus. So we already discussed this na, Tm or Tw minus Tm. Tw minus Tm upon Tw minus Tmi is equal to e to the power minus h px upon m dot cp, right? And at x is equal to L, Tm becomes Tmi. Sorry, Tm becomes Tme. So Tw minus Tme upon Tw minus Tmi is equal to e to the power minus hpl upon, this is m dot cp. Okay, so h value is h value what is the value of h? 113.3, right? 113.3 watt per meter square Kelvin. This is the value of h, and value of h, yes, 113.3, yes. So option number C is correct. Statement C is correct. Now come to the length of the annulus. Okay, so Tw minus Tme. So Tw is given, Tw is 75. 75, Tw is 75. So 75 minus and exit temperature is 50. So 75 minus 50 upon 75 minus and Tmi is 25. And this is e to the power minus h value. So what is the value of h? That value of h is 113.3. 113.3 into. Now tell me what is perimeter? Okay, tell me what is perimeter? What is the perimeter? In this case, what is the perimeter? The heat transfer occurs. Perimeter from where heat transfer occurs. Basically, P into L is surface area is nothing but the. So heat transfer occurs from this na, pi into di. Right, pi into di. This is pi into di, and di is 0.04. 0.04 into length. Length value is given. Okay, length is unknown, sorry. Divided by mass flow rate. And mass flow rate. So velocity is given, mass flow rate is not mentioned. So first you calculate the mass flow rate, right? So mass flow rate is m dot is equal to rho into area. So area is pi by 4, 0.06 square minus 0.04 square, pi by 4 d square, right? Rho into area into velocity, and velocity is 30. So what is mass flow rate? Right, mass flow rate. So density is 1.07 into 0.785 into 0.06 square minus 0.04 square into 30. So I think this comes 0.05039 kg per second. Beta, please check mass flow rate. Everyone getting this? 0.05. Right, so 0.05 kg per second into Cp, and Cp value is given 1005. 1005. Yes. And if you take log both side, so ln 75 minus 50, 25, and 75 minus 25, 50 is equal to minus 113.3 into pi into 0.04 into length upon 0.05 into 1005. Right, so ln 25 by 50, 1 by 2 means, right, into 0.05 into 1005, 1005, 0.05, 1005, and this is 113.3 into pi into 0.04. So L comes 2.446 meter. Please check beta, everyone getting this? L is 2.446 meter. Yes, 2.44 meter. This is the L. So only C is correct. Right, only C is correct. So this is also wrong. Right, only C is correct. Yes. Is it clear to everyone? Is it clear? Okay. See this question. सर ऐसे क्वेश्चन में एग्जाम में कितना टाइम लग, देखो कुछ क्वेश्चंस ऐसे होते हैं जिसमें थोड़ा सा टाइम लगता है ना। कुछ क्वेश्चंस ऐसे होते हैं जिसमें देखो अभी आप इसमें आपके पास दो चीजें चल रही है, एक दिमाग भी आप लगा रहे हो, कैलकुलेशन भी कर रहे हो, तो कुछ क्वेश्चंस डेफिनेटली लेंदी होते हैं एग्जाम में, ठीक है। मतलब ऐसा नहीं होगा कि आपके पास क्वेश्चन में आपके पास सारे क्वेश्चंस इजी रहे, मतलब सारे क्वेश्चंस आपके पास आई कैन से कि जल्दी जल्दी बन जाएंगे, कम स्टेप्स में हो जाएंगे, ऐसे नहीं, कुछ क्वेश्चंस ऐसे मिलेंगे और हमेशा होता है वो, है ना। तो समझदारी इसी में होती है कि ऐसे क्वेश्चंस को आप बाद में अटेम्प्ट करो, राइट, ऐसे क्वेश्चंस को आप बाद में अटेम्प्ट करो, ठीक है। स्टार्टिंग में तो नहीं अटेम्प्ट करो ऐसे क्वेश्चंस को, बिकॉज उसमें टाइम लगेगा। आप खुद देख पा रहे हो, इफ यू सी दिस क्वेश्चन, राइट, देन इन दिस क्वेश्चन, right, in this question convective heat transfer coefficient is asked, in this question length of the annulus is asked, so definitely it is time taking question, right। so समझदारी क्या बोलती है, समझदारी तो यही बोल रही है ना कि इस क्वेश्चन को मैं बाद में करूँ, अगर मेरे पास टाइम बचेगा तो मैं करूंगा, नहीं बचेगा तो उस टाइम पे मैं छोड़ दूंगा। so every year in your paper 1 or 2 questions are such type of questions, right, which are lengthy। okay, so that's why I'm saying ना, ठीक है, समझदारी क्या है, उस समय उस क्वेश्चन को छोड़ो, बिकॉज आपके पास ये जो एग्जाम है, ये एग्जाम आपके पास सिर्फ ये चेक नहीं करता कि आपको कितना आता है, ठीक है। आपके पास जो गेट का एग्जाम है, गेट का एग्जाम आपको ये नहीं चेक करता कि आपको कितना आता है। अगर मैं आपके पास एक पेपर है, ठीक है, पेपर आपके पास 3 घंटे का पेपर है, अगर उस पेपर के लिए मैं आपको 4 घंटा दे दूं तो ऑब्वियसली आप ज्यादा क्वेश्चन सॉल्व कर पाओगे। सो मोस्ट इंपॉर्टेंट थिंग इज कि विद इन द टाइम डोमेन, विद इन द टाइम फ्रेम, जो भी आपको टाइम दिया गया है, उस टाइम में आप कितना, ठीक है, समझदारी से चीजों को टैकल करते हो, ठीक है, ये भी आपके पास चेक होता है। सो हर साल आपको ऐसे क्वेश्चंस मिलते हैं, ठीक है। इवन when you are dealing with the test series, in your test series also you are getting 1 or 2 questions which are actually little bit lengthy, ठीक है। तो समझदारी तो यही है, ठीक है, उस टाइम पे आपके पास ये समझना जरूरी है कि कौन से क्वेश्चन को मेरे को, ठीक है, उस टाइम पे छोड़ देना है, मैं लास्ट में मेरे पास टाइम बचेगा तो मैं करूंगा। ये भी बड़ा इंपॉर्टेंट होता है गेट के पेपर में, सिर्फ गेट के पढ़ के जाना ही सफिशिएंट नहीं होता है, राइट। ओके, ओके, नाउ सी दिस क्वेश्चन। सर वो चालू कर दिया था, ये सब नहीं था क्या? कौन सा था? एक मिनट मैं देख लेता हूँ, मेरे दिमाग से निकल गया, कौन सा था? आई थिंक ये वाला था क्या? ओके है, यस। ओके 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 फाइन, ट्राई टू सॉल्व दिस वन। ओके 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 फाइन फाइन, ट्राई टू सॉल्व दिस वन। ठीक है, इसको सॉल्व कर लो। यही था ना क्वेश्चन? एक बार बताओ, यही था कि कुछ और था? There is a long fin of 10 millimeter dia dissipates 30 watt by force convection to air in the cross flow. If the diameter of the fin is doubled and the all other condition remains same, then the rate of heat transfer is, yes. Okay, so we have the long fin, diameter is 10 millimeter, है ना? And dissipates 30 watt by force convection to air in cross flow. So basically we have long fin like this, right? And diameter is mentioned, diameter is given 10 millimeter, right? And flow occurs like this, right? Flow of fluid occurs like this. Okay, cross flow you can say like this, no issue. Okay, if the diameter of the fin is doubled and all other condition remains same, then the rate of heat transfer. So in question it is clearly mentioned long fin, right? In this question it is clearly mentioned fin is long. So if fin is long, एक minute, sir 2000, if 2000, then how the transition in Reynolds number, how is turbulent? तो हमेशा for turbulent flow. बेटा ये बताओ मेरे को, अगर आपके पास 2000 से जितने भी क्वेश्चंस आपने किए हैं उसमें आपके पास जो रेनॉल्ड नंबर की वैल्यू 4000 से ज्यादा आ रही थी ना, राइट? देखो आपके पास जो एक्सप्रेशंस अवेलेबल है, दोज एक्सप्रेशंस आर फॉर आइदर इट इज फॉर द लैमिनार और टर्बुलेंट, राइट? सो जितने भी क्वेश्चंस हम लोगों ने अभी हम सॉल्व किए, जितने भी क्वेश्चंस हम लोगों ने सॉल्व किए, उन क्वेश्चंस में आपके पास क्या था? उन क्वेश्चंस में रेनॉल्ड नंबर की वैल्यू आपको अगर आपके पास लैमिनार है तो 2000 से कम है, इफ इट इज मोर देन इफ रेनॉल्ड नंबर वैल्यू इज मोर देन 4000, तो आप लोगों ने देखा है कि मैक्सिमम केस में आपके पास 4000 से ज्यादा ही आ रहा था, तो डायरेक्टली मैंने बोला कि अगर ग्रेटर देन है 2000 से तो उसको आप टर्बुलेंट ले लो। ट्रांजिशन के केस में आपके पास कोई फॉर्मूला अवेलेबल नहीं है ना, या तो ट्रांजिशन के केस में आपको देना पड़ेगा। तो इवन आपने जितने भी प्रॉब्लम्स आपने सॉल्व किए उसमें तो 4000 से ज्यादा ही आया था। जितने भी क्वेश्चंस आपने सॉल्व किए हैं उसमें जो रेनॉल्ड नंबर की वैल्यू जो आपको मिली है वो 4000 से ज्यादा ही मिली थी। ठीक है, ओके ओके। सो दिस इज अ लॉन्ग फिन, एंड इन केस ऑफ द लॉन्ग फिन, in case of the long fin, right, rate of heat transfer is root over hp kac, and this is theta b, correct? Q dot is root over hp kac theta b. So it is very much clear your Q dot, right? Q dot is directly proportional to, Q dot is directly proportional to, right? You can say it is directly proportional to root over, or just 1 minute, h, and perimeter you can write this is pi d, thermal conductivity is k, and this is pi by 4 d square, and this is theta b, right? So Q dot is directly proportional to, right, s to the power 1 by 2, right, and also it is proportional to d to the power 3 by 2, because you are changing the diameter na. If the diameter of the fin is doubled, okay, if you are changing the diameter, so this is d to the power, right, d to the power, this is d to the power 3, so this is 3 by 2, right? So Q1 by Q2, you can write Q1 by Q2 or Q2 by Q1 basically. Q2 by Q1 is equal to, this is H2 by H1 to the power 1 by 2, and this is D2 by D1 to the power 3 by 2. Correct na? Okay, so D2 is 2 times of D1. Now tell me what is H? What is H? So Nusselt number expression is given, and the Nusselt number expression is Nusselt number directly proportional to Reynolds number to the power A and Prandtl number to the power B. Okay, so when you are changing the diameter, Prandtl number is not changing na, because Prandtl number only depends on the thermophysical properties of the fluid. Okay, so Nusselt number is directly proportional to Reynolds number to the power A and Reynolds number to the power A, and A value is 0.47. This is 0.47. So when you open the Reynolds number, this is rho, this is U average diameter divided by mu. Correct. And when you are changing the diameter actually, and flow is, there is a fin and a flow occurs perpendicular to the fin. So characteristic dimension is D only. So you can write Nusselt number is directly proportional to, this is rho U average D, or just 1 minute, you can write, open Nusselt number also na, H D by KF, right? H D by KF, and directly proportional to, this is rho U average D upon mu to the power 0.47. So you can write H is directly proportional to, right, this is D to the power 0.47 upon ND. So what you are getting? You are getting H is directly proportional to D to the power, and this is 0.53, right, 0.53 minus 0.53, right? H is proportional to D to the power 0.47 minus 1. So this is minus 53. Okay. So Q2 by Q1, Q2 by Q1 is equal to, it is H2 by H1, H2 by H1 to the power 1 by 2, and it is D2 by D1 to the power 3 by 2 na, 3 by 2, yes, 3 by 2. Okay, if you see here, H1 by H2 or H2 by H1, so H2 by H1 is nothing but the, you can write H2 by H1, you can write D1 by D2 to the power 0.53. So this is D1 by D2 to the power 0.53, and D2 by D1 to the power 1.5, right? Or you can write D2 by D1 to the power 1.5 minus 0.53. So it is 0.97. Right, and Q2 is unknown, Q1 is 30, and D2 is 2 times of D1 na? D2 is 2 times of D1, double. So this is 2 to the power 0.97. Right, so 2 to the power 0.97 into 30. 58 point something? 70.61. 0.53 by 2 होगा, कहाँ पे होगा? 1 मिनट मैं देख लेता हूँ, कहीं पे मिस्टेक किया है क्या मैंने? जस्ट 1 मिनट, कहाँ पे मिस्टेक किया है मैंने, एक बार चेक करते हैं. Q2 by Q1, and this is D to the power 3, so 3 by 2, this is fine. H to the power 1 by 2, so H2 by H1, D2 by D1, fine. Q2 by Q1. Okay, so Nusselt number is directly proportional to Reynolds number to the power 0.47. This is also correct. And rho u average d by mu and d. So d to the power 0.7 d. H is directly proportional to d to the power minus 0.53. This is also fine. H2 by H1. So H2 by H1 is d1 by d2. d1 by d2 to the power 0.53. This is also correct. So H2 by H1. And yes, there is the error 0.53 by 2. 0.53 by 2. Yes, there is an error 0.53 by 2 and 1.5 minus 0.53 by 2. So it is 1.235. It is 1.235. Right, 1.235. Right, so 30 into 2 to the power 1.235. 70.614. Right, 70.614. Yes, 70.614. 70.614 watt. Yes, 70.614. Is it okay? Okay. Now see the next question. Now see the next question. सर फीन में फ्लो का डायरेक्शन क्रॉस फ्लो बोला तो है बेटा, क्रॉस फ्लो तो है, ठीक है। फीन का जो आपके पास एक्सियल डायरेक्शन है उसके परपेंडिकुलर फ्लो हो रहा है, बोला तो है। इन क्वेश्चन इट इज मेंशन ना, इन क्वेश्चन इट इज मेंशन ना, इट इज क्लियरली मेंशन ना, क्रॉस फ्लो। ओके, now see the next question. हाँ, फॉर्मूले में क्या चेंज आएगा? फॉर्मूला इज सेम, एच वैल्यू चेंजेस। अरे आपके पास क्रॉस फ्लो होगा या पैरेलल फ्लो होगा या काउंटर फ्लो होगा, उससे आपके पास एच की वैल्यू पे फर्क आएगा ना, एच वैल्यू चेंजेस ना, एच वैल्यू चेंजेस। हाँ, फॉर्मूला जैसा भी होगा सेम ही रहेगा। उस फॉर्मूले में जो एच की वैल्यू है, एच की वैल्यू पे चेंज आएगा। ओके, hollow cylinder of equal length, hollow cylinder of equal length and inner radius L is equal to D is sealed at both ends with flat plate as shown in the figure. If the its inner surface A1, A2, A3 radiate energy Fij denotes the fraction of radiation energy leaving the surface Ai which reaches to the Aj. Okay, it is also known that F13, 3 minus 2 root 2. Which one of the following is correct? So basically F21 is asked. Right, F21 is asked. F21. So F13 is given, na? Right, F13 is given. And F13 is 3 minus 2 root 2. 3 minus 2 root 2, right? So if you write summation rule for the surface 1, F11 plus F12 plus F13 is equal to 1. And F11, so basically 11 is a flat surface. So F11 is 0. Right, F12 plus F13 is 3 minus 2 root 2 is equal to 1. So F12 is 1 minus 3 plus 2 root 2. So this is 2 root 2 minus 2. Right, this is F12. Right, but in this question what is asked? In this question F21 is asked. So if you apply the reciprocity, so A1 F12 is equal to A2 F21. Right, so F21 is equal to A1 by A2, and this is F12. Right, and A1 is simply pi by 4 d square. A1 is pi by 4 d square upon, and A2 is curved area, so that is pi dl, and L is equal to d, so pi dl, so pi d square. Right, L is equal to d na, into F12, and F12 is 2 and root 2 minus 1. Right, pi d square, and this is 2 and this is 2. So what you are getting, this is F21 is equal to this is root 2 minus 1 divided by 2. Root 2 minus 1 divided by 2. This is the F21. F21 is root 2 minus 1 divided by 2. So correct option is option number B. Option number B is correct. Right, correct option is option number B. Option number B is correct. Right? Yes. Okay, now can you complete this shape factor matrix? In same problem, if I ask shape factor matrix, in the same problem, if I ask complete the shape factor matrix. So shape factor matrix, so basically this is 3 surface enclosure, and in 3 surface enclosure, if you write the shape factor matrix F11, F12, F13, right, F21, F22, F23, F31, F32, F33. Can you complete the shape factor matrix? So F11 is 0. Right, F11 is 0. F12. So F12 is 2 root 2 minus 2. So 2 root 2 minus 1. And F13 is already given 3 minus 2 root 2. 3 minus 2 root 2. Now F21. So F21 is root 2 minus 1 by 2. Root 2 minus 1 by 2. Now F22. So can you find the F22? What is F22? So to find out the F22 for surface 2, can you write summation rule F21 plus F22 plus F23 is equal to 1. Right, F21 plus F22 plus F23 is equal to 1. Now F21 is root 2 minus 1. Right, root 2 minus 1 by 2 plus F22 is unknown. And F23. So F23 is equal to F21 only, right? F23 is equal to F21 only. F23 is equal to F21 only from the symmetricity, right? From the symmetricity, F23 is equal to F23 is equal to F21, and F23 is root 2 minus 1 by 2. This is root 2 minus 1 by 2, right? So F22, right? F22. So this is 1 minus, right? 1 minus, and this is root 2 minus 1, right? So 1 minus root 2 plus 1. So basically this is root 2. F22 is root 2, right? Just 1 minute, just 1 minute. F21 is equal to F23. So F21 is equal to F23, and F21 is root 2 minus 1 by 2, correct? Huh? So root 2 minus 1 by 2, F22, and root 2 minus 1 by 2. Okay, so this is 2 into root 2 minus 1. 2 into root 2 minus 1 by 2. 2 to cancel out, root 2 minus 1. 1 minus root 2 minus 1. So 1 minus root 2 plus 1. Sorry, this is 2 minus, I'm sorry, this is 2 minus root 2. Right, this is 2 minus root 2. So this is F22. F22. So this is 2 minus root 2. 2 minus root 2. And F23. So F23 is F21 only. This is root 2 minus 1, root 2 minus 1 by 2. Okay, now F31. So F31 is equal to F13. F31, F31 is equal to F13. F31 is equal to F13. Right, F31 is equal to F31 is equal to F13 from the symmetricity. 3 minus 2 root 2. Right, this is 3 minus 2 root 2. 3 minus 2 root 2. Right, and F32. F33 is 0. F33 is 0. So F32 is 1 minus, right? F32, F31 plus F32 plus F33 is equal to 1. So F31, 3 minus 2 root 2 plus F32 is unknown, and F33 is 0, 1. So F32, right? 1 minus 3 plus 2 root 2, right? So this is 2 root 2 minus 2, right? So this is 2 root 2 minus 2. Please check, beta, everyone getting this shape factor matrix? Please check, everyone getting this? Please check, everyone getting same shape factor matrix? And if you want to cross verify, see, 2 root 2 minus 2 root 2 minus 1. Sum of the row element is equal to 1, na? Sum of the row element is equal to 1. So 2 root 2 minus 2 plus 3 minus 2 root 2. So 1. Root 2 minus 1 by 2 minus 2 root 2, root 2 minus 1 by 2 plus 2 minus root 2 and root 2 minus 1. So 2 minus root 2, yes, this is also correct. 3 minus 2 root 2, 2 minus root 2. Okay, this is also okay. Right, sum of the row element is equal to 1. Sum of the row element is equal to 1. Okay, now see the next question. Simple question. Okay, so this is a simple question based on the this is the simple question based on the energy balance. How many questions left? Okay, remaining question we will discuss in Abhyas. Right, remaining question we will discuss in Abhyas. So a fluid flows over a heated horizontal plate maintained at a temperature TW. The bulk temperature of the fluid is T infinity. The temperature profile in the thermal boundary layer is given by T is equal to TW plus TW minus T infinity 1 by 2 y by delta T cube minus 3 by 2 y by delta T. Okay. Y is the vertical distance from the plate. Delta T is the thickness of the thermal boundary layer. K is the thermal conductivity of the fluid. The local heat transfer coefficient. Right. Local heat transfer coefficient. So simply if you apply the energy balance, right, if you apply the energy balance directly you can write, right, this is minus kf or minus k dt by dy, this is kf only, dt by dy y is equal to 0 is equal to this is hx and this is tw minus t infinity. Okay, now dt by dy, so the dt by dy at y is equal to 0, so 0 plus tw minus t infinity and this is minus 3 by 2 delta t. So this is dt by dy at y is equal to 0. So minus k into tw minus t infinity and this is minus 3 by 2 delta t is equal to hx tw minus t infinity. Right. So tw minus t infinity is cancel out. Right. So hx is equal to this is 3 by 2 k by delta t. Right. 3 by 2 k delta t. So correct option is option number C. Correct option is option number C. Option number C is correct. Right. Correct option is option number C. C is the correct one. Fine. So see you guys in Abhyas classes. हीट एक्सचेंज करेंगे अभी, हीट एक्सचेंजर करवाया नहीं है ना, मैंने हीट एक्सचेंजर का मैंने रिवीजन नहीं करवाया था, सो इसलिए मैंने हीट एक्सचेंजर के सम्स इसमें है नहीं। वैसे एनीवेज आप कर लोगे, ठीक है, क्योंकि रिवीजन ही करवाना है, सो एनीवेज वो हम लोग अभ्यास वाली क्लास में कर लेंगे। ठीक है, हीट एक्सचेंजर के जो सम्स हैं वो हम लोग अभ्यास वाली बैच में कर लेंगे, अभ्यास वाली क्लास में। हीट एक्सचेंजर का सम्स नहीं, इसमें नहीं था। ओके, ठीक है, फिर अभ्यास वाले बैच में मिलते हैं। सो थैंक यू सो मच, बाय बाय, टेक केयर।